Hello and welcome back. We are continuing with our study in numerical linear algebra. We have seen some methods which are like the direct methods for solving linear systems of linear equations. What we intend to do today is to look at some of these iterative methods which are reminiscent of the iterative methods that we have used to solve our equations in one variable. So let me start sharing the slides for the lecture today. All right, I hope you can see the slides now. So we are going to discuss these iterative techniques to solve systems of linear equations. Just a point to be emphasized, which is that if you are working with linear systems of small dimensions, then it's unlikely that these iterative techniques will be used, because then the time required for sufficient accuracy for iterative techniques is actually more than that required for direct techniques if you're using linear systems of small dimensions. So for small dimensions, say dimension 3 or dimension 4, we would normally go for direct systems. But when you have a huge data, a big number of system equations and big number of variables, then you would go for iterative techniques. So there are two main techniques that we are going to study. There is the Jacobi method and there is a Gauss-Seidel method. So these are methods which date to the late 18th century, 18th and early 19th century. So what does an iterative technique do? To solve such a system Ax equal to b, it starts with an initial approximation to the solution. So what we do is that we start with an initial approximation x naught, and then we generate a sequence of vectors xk, where k goes from 0 to infinity, such that this vector converges to x. So this is what we would try to do. Whether it is possible for all systems or if it's possible for some systems, we will see that in this lecture. So let's look at the Jacobi method. We start with an assumption. Of course, we will need to have that determinant A is non-zero because we want our matrix to be invertible, but we also need that the diagonal entries of the matrix are also non-zero. In fact, if you write the equations, each equation in the system reads as the summation aij xj equal to bi. So you have the ith equation, which is given by aij xj equal to bi, or if you take out the xi variable, it will be aii xi equal to bi minus summation j, where j is different from I, aij xj, and then you can divide by the aii. We have assumed above that the diagonal entries are non-zero, so you can divide by aii. So what this says is that xi can be written as bi minus summation aij xj, where j is different from I, whole thing divided by aii. So you can write xi in terms of the other xj and the constant bi as well as the coefficient aii. This will allow us to do the iterations. What we'll do is that when we have started with this initial vector x0, which is given by x10 up to xn0, and taking the transpose, so it's the column vector. Then for the kth approximation and its ith component, we put the k minus 1 approximations in the above equation. This equation that we had, xi equal to bi minus summation aij xj, where j is different from I, whole thing divided by ai. In that, you put the components xj for the k minus 1 approximation and compute the kth approximation xi, the ith component, using this formula. This is what we do. This was suggested by Jacobi. It's a very simple idea, but it works quite well. So for instance, if your x, which is x1, x2, xn transpose, is answer to the system, if this is the solution, then let's compute the error that we are likely to get. So first of all, we have the ith component of your solution xi, difference is equal to summation aij upon aii xj minus k, the xj of k minus 1. So let me explain this once again to you. The xi with all the other xj's of the correct solution will satisfy the ith row, ith equation. So you will have that this xi is bi minus summation aij xj upon aii, where the j is different from I. And xi k is defined to be bi minus summation aij xj for k minus 1 upon aii. So when you take the differences of those two right hand sides, you will have cancelled the bi's. The xi for k, I think there might be a minus sign somewhere here, but ultimately we are going to take the modulus of this, so it should still be okay. So up to a negative sign, what we have is that the left hand side can be expanded out to get the right hand side, and the bi will be cancelled. So when you take the modulus, this is, we will put a modulus for these parts inside the bracket, and then you will get a less than or equal to sign. So this xj minus xj k minus 1, this is jth component of the vector xx minus xk minus 1. The k minus 1th approximation and x, you take the difference of these two vectors. The jth component of that vector is the one that is highlighted here in the slide. And if you look at the maximum among all these as j goes from 1 to n, that is the L infinity norm. So what we have is that this whole thing is going to be less than or equal to, where we replace this bracket under modulus sign by the L infinity norm by taking the maximal one. And so this is what we have, and this aij upon aii, that comes out from. So we have the ith component of x minus xk is under modulus sign less than or equal to L infinity norm of x minus xk minus 1. So this is the distance of xk minus 1 from x. And we have the ith component of the kth approximation subtracted from the ith component of xi. Now this right hand side is independent of I. Therefore this inequality is valid for all I going from 1 to n. So you might take the maximum on the left hand side, which will give us the L infinity norm for x minus xk, and we will still have the inequality being valid. So you have that x minus xk L infinity norm is less than or equal to x minus xk minus 1 L infinity norm into, only thing was that here you had an I which was fixed. So instead of that I, we will now take all possible of these expressions and take the maximum. So this is what we have when we take the L infinity norm on both the left hand side and the right hand side. So what we now have is that the error for the kth approximation is bounded above by the error in the k minus 1th approximation times, now this is the number which is truly independent of I. So we will give a name to this. We call this number to be mu. It is summation aij upon aii in the modulus sign, and then you take the maximum as I varies. If this mu is less than 1, then the convergence is guaranteed, because whatever distance you have here, you are going to make it smaller by multiplying by mu. So this right hand side actually goes to 0. If mu is less than 1, at every step you are going to multiply by 1 extra power of mu. So you will have x minus x0 L infinity norm. The x minus x1 L infinity norm is less than or equal to the 0th error times mu. The second error is less than or equal to the first error times mu, which is less than or equal to the 0th error times mu square. As for mu less than 1, the powers go to 0. We will have that the errors ultimately go to 0, and therefore the convergence is guaranteed when we have the Jacobi method. This condition will relate to summation aij for j not equal to I being less than mod aii for every I. So what it says is that when you look at the ith equation, the diagonal element in the modulus sign is bigger than the moduli of all other elements in the same row being summed. And if you remember, this is nothing but a strictly diagonally dominant matrix. So our strictly diagonally dominant matrices have shown up here, and when you have this condition, then you do have that the Jacobi method gives you a solution. So for instance, let's take an example. We have this matrix here. We check quickly that this is strictly diagonally dominant because for the first row, the sum of the non-diagonal entries is 2 plus 3, whereas we have the diagonal entry to be 10. In the second row, the sum for non-diagonal entries under modulus sign is 1 plus 1 plus 3, which is 5, and the diagonal entry is 11. In the third row, the diagonal entry is 10, and you have 2 plus 1 plus 1, 4. And finally, in the fourth row, the diagonal entry is 8, whereas the sum of the non-diagonal entries under modulus sign is equal to 4. So we are guaranteed to get a solution in this, and we start with 0, 0, 0, 0 as our approximation, and now we find the kth approximations xk. So I will not give all the results here. I will actually give you a table later on in our same lecture. But let me write some of the initial terms. So you have that the 0th approximation is 0, 0, 0, 0. First approximation is 0.6, 2.2727, minus 1.1 and 1.875. And so on up to the 10th approximation being 1.001, 1.9998, minus of 0.9998 and 0.9998. So it is reasonable to expect that the solution is 1, 2, minus 1 and 1. That's what the solution is, 1, 2, minus 1, 1. And already in 10 steps, we have gone closer to the solutions in the sense that the error is 10 less than 10 power minus 3. So this is what we have been able to achieve. Now, as is really very common for the 19th century mathematics, Gauss had a better method up his sleeve. So you know Gauss, Carl Friedrich Gauss, a very brilliant mathematician. He is called Prince of Mathematics for the brilliant methods that he brought to solve some of the very interesting problems in mathematics. It is said that whenever someone would go to him showing their own research, then Gauss would look for some paper in his drawers and show that person that he had done it some 10 years back, but did not bother publishing it. So this is something which happened quite frequently with Gauss, and Gauss had a very nice method here also. But again, this he did not bother publishing. What he did was that he mentioned it in a private correspondence with his student in 1823, and it was published only later in 1874. We see that Jacobi, I gave it in one of the earlier slides, Jacobi suggested his method in 1838 or so, which was after Gauss mentioned his method. Okay, so already Gauss had a better method before Jacobi, but this method was worked out by Seidel on his own, and so we call this Gauss-Seidel method. I think this is very nice that we are giving credit to both the people who discovered it on their own. It would be nice to see if this happens every time, especially when some Indians have done something centuries before, and if they are given a due credit to that with all the evidence being available, then that would be something really nice. Okay, so let's see what is Gauss-Seidel method. What Gauss said was the following. He said that you have improved upon the first component of xk. So you have xk minus 1 with you. You use that to compute x1, the first component of xk. Then, while talking about the second component of xk, you will have a linear combination of all the other components other than the second. He said that instead of taking the first component of k minus 1, you take the first component of k1 because that is improved. That's supposed to be better. And so on. So let me explain this again. The components of xk minus 1 are used to compute all components xik of xk. This is the Jacobi method. But already you have computed x1 up to xi minus 1 of the new approximation, and they are expected to be better than the k minus 1 approximation anyway. So for x1, x2, xi minus 1 to the actual solutions, these are supposed to be better, the kth one. Then it is reasonable to use xik using these, compute xik using these most recently calculated values. So what you would do is that for computing the ith component of the kth approximation, you use first, second up to I minus 1 approximation to the kth vector, and then I plus 1 onwards you would anyway go to the components of the k minus 1 vector. This is what Gauss and Seidel suggested. So suppose we use our earlier example and we solve the method, the example, the earlier system by Gauss-Seidel method. Let's see if we can improve. So this was our earlier example with the strictly diagonally dominant matrix. Again we start with 0, 0, 0, 0, and now we want to find approximations for xk using Gauss-Seidel method. Zeroth approximation is anyway 0. First approximation, you will notice that x1 1 is the same because you are going to use all 4 approximations of the zeroth method. But the second one already is an improvement, 2.3272, whereas that one was 2.2727. There is already a change, and instead of minus 1.1, we get minus 0.9873 and then 0.8789. So although for some initial values it may not seem that we are doing an improvement, but already by the 5th approximation we have reached the correct solution, 1, 2, minus 1 and 1. Whereas in the Jacobi method we had to go to the 10th approximation to get this value. Right, so already in the 5th approximation we have the correct solution in the Gauss-Seidel method. So if we were to compare Jacobi vis-a-vis Gauss-Seidel, these are the top one is for the Jacobi and the lower one is for Gauss-Seidel. We notice that we are going to get zeros in the first decimal point after in the first digit after decimal point in all 4 by the second Gauss-Seidel approximation. To get that 0 in the first approximation up to the after the decimal point, we had to go to the 3rd approximation, because in the second one you see here we have 1.7 instead of 2, 0.8 instead of 1 and 0.88 instead of 1. So we do not get a first decimal point digit as 0 in the second. We have to go to the 3rd one to get, even there the 4th one is not quite 0, but if you go to the 4th one, then surely. So in the Gauss-Seidel method, it's enough to go up to the 2nd approximation if you were to get the error to be less than 1 upon 10. But in the Jacobi method, you have to go all the way to the 4th approximation. And if we take the further computations here, we see that already the 5th approximation or even the 4th approximation is giving you the error to be less than 10 power minus 3. Whereas for that, here you have to go at least till 9th approximation, if not the 10th approximation. Okay, so the Gauss-Seidel is definitely doing better than the Jacobi method. So it does imply that Gauss-Seidel method is superior to the Jacobi method. That is what appears, and this is almost always true. The reason being that there are linear systems for which the Jacobi method converges, but the Gauss-Seidel method does not converge. We will try to see some examples in our tutorials, and we will see why this happens. But whenever we encounter linear systems of this type, they will correspond to matrices which are not strictly diagonally dominant, because if A is strictly diagonally dominant, then for any choice of the initial vector, both Jacobi and Gauss-Seidel methods will give sequences which converge to the unique solution. So whenever the system is given by a matrix which is strictly diagonally dominant, we are guaranteed of getting the convergence by both Jacobi and Gauss-Seidel. However, whenever we do not have a strictly diagonally dominant matrix, it is not guaranteed that our methods will give convergence. In fact, sometimes Jacobi method will converge and Gauss-Seidel will not, and sometimes Gauss-Seidel method will converge but Jacobi will not. So we will try to see these examples in our tutorials, and we will, after this lecture, we are going to talk about ill conditioning of the matrices. After all, it's an equation, it's a problem which is given to us, and the stability issues are there for this problem also. So we would like to discuss whether these problems are well posed, and we need to introduce new concepts for this. So we would try to do in our next lecture and stop this lecture for a short time, only 20 minutes or so, and see you in our next